Hello and welcome back. We're finally moving on to Chapter 10, dealing with weathering, mass wasting, and erosion. Basically, these are external forces acting on rock materials over time to create the types of landforms that we see today. So, weathering, mass wasting, and erosion, those are the three main components of these external processes. Weathering means the breaking up of rock by physical, chemical, or biological means, so breaking up big rocks into smaller rocks. Mass wasting means gravity doing most of the work, pulling down rock material from high places to low places. And erosion refers to the removal and transportation of this loose material, again, from higher places to low places. But rather than just by gravity, this is aided by the presence of flowing water or wind or ice. So we'll look at these individually here in just a second. So again, weathering, physical weathering, the mechanical breaking down of rock material, chemical weathering, the decomposition of rock through chemical change, and biological weathering is the breaking down of rock material by the use of plants or animals doing the work. Now, as we can see here, physical weathering is itself broken down into three different types. One is called frost wedging or freeze-thaw action involving ice. We have salt wedging, which involves the growth of salt crystals within the cracks of rocks, and as they grow, they crack the rock open. And erosional unloading, otherwise known as exfoliation. This is due to rocks being formed at depth and being brought to the surface where there's less pressure. More on that to come. Chemical weathering, also broken down into three categories. Oxidation means the chemical decomposition of the rock material involving the addition of oxygen atoms into the matrix of the minerals within the rocks. And as the oxygen gets added, it weakens the rock. Hydrolysis is a very similar process, but it involves water being added to the chemical composition of the rocks and minerals, thereby weakening them. And carbonation involves carbon dioxide reacting with the rock materials to dissolve certain rocks and then deposit that same mineral content in other places. We'll see more about that coming up. And then biological, two different types of biological weathering. Root wedging, where the roots of trees and plants kind of break open or physically wedge apart rocks, and the actions of burrowing animals. So as they make their burrows and holes like worm paths through soil, that's going to allow more oxygen and water to react with the rock material that they've been burrowing through. So here we see an example of physical weathering, this particular type, frost wedging. Now what we can see here is that there are natural cracks within rocks. We call these joints, and these natural weak points can be exploited as water would accumulate in there. So imagine if there was overnight a little bit of drizzle or rain, it gets into the cracks between the rocks. And overnight temperatures, of course, get colder and colder into the early morning hours. Well, that water could actually freeze. When water freezes, it expands, and that's going to basically wedge open that gap between that existing gap between portions of the rock on very, very fine scales to sometimes on the order of meters apart. These joint spaces can be very variable. And as the water gets into those joints, the water expands and we see the physical breaking apart of that rock material due to ice. So we refer to that as frost wedging. This is a result of frost wedging. You can see there would have been a joint in the location I'm highlighting, or maybe it's not showing on my cursor. Let's see if I can do that. Here we go. So in this area right here, we would see water would have existed in the past and frozen and cracked open that rock. It takes a long time for this to happen. It's subsequent freezing and freezing and thawing over different occasions. Now the same can be said in this case here. We have a rock that has been broken up physically by the presence of salt crystals growing into the cracks within a rock. Over time, as the salt crystals grow, they expand and they bust open or crack open or physically break open that rock material. This is typically found in dry areas and in this case, a desert environment. And our third type of physical weathering is referred to as exfoliation, or erosional unloading. Now, what this diagram is showing, of course, there's no dinosaurs around anymore, but in the time of the dinosaurs, so maybe more than hundreds of millions of years ago, we would have had rock material that was covered over by thousands of feet of other rock material. Now, over time, this rock material would have been, or could have been, uplifted towards the surface, and everything above it eroded away. So finally, we expose that rock material in modern times to the surface. All of the pressure of the overlying rock that used to be there no longer exists because those rocks no longer exist. Because this rock material was formed under such pressure, it also was exerting an outward pressure to balance the overburden. Well, once we lift this to the surface, only that outward pressure exists. And so rocks often, when lifted towards the surface, will peel off in these onion-like layers, the process being called exfoliation. You can see this quite often when granitic bodies, remember granite is an igneous intrusive rock, when that is moved to the surface over millions of years, we often see this erosional unloading or exfoliation exhibited at the surface. It could look like this. So these are granitic rocks that were formed deep in the crust, moved towards the surface, and because there's no longer any overburden, well, we're seeing that onion-like exfoliation occur. So that's a third of our physical weathering processes. We now move on to chemical weathering, three of these to talk about. The first one is oxidation. Now in this diagram here, we can see a rock. The lighter color on the rock is probably a granitic type rock that has not been weathered, but the outer exposed area was subjected to interacting with oxygen in the air, in the atmosphere. So oxygen will find its way into the cracks and pores of this exposed portion of the rock and interact with the mineral matter there. And the oxygen atoms will actually bond to some of the minerals to create other minerals. So in this case here, we've got the iron that the iron in the unweathered portion. You cannot see the iron color because it has not yet been exposed to oxygen, but once the iron minerals are exposed to oxygen, they form iron oxide. So they basically rust in place. And as it rusts, just like as metal rusts out in maybe a bicycle left out for years in the backyard, it weakens the metal. In this case, it would weaken the rock material. So rocks get weakened chemically by the addition of oxygen. And in this case, we refer to the rocks as being oxidized through the process of oxidation. Oxygen being the key element interacting with the rock materials. The same can be said when water interacts with certain minerals and rocks along, in this case, this is along the natural joint planes. Those are planes of weakness, and now water can get into those very much easier than getting into the depth of the rocks themselves. And basically, it's changing the chemical composition of the rock by adding H2O to the mineral content of those rocks. And the resultant rocks are always weaker. Sometimes they expand, making them also become weaker. So over time, what we would see in a case like this are that some of these rocks would become a little bit more rounded and rounded as the outer edge has been exposed to oxygen, but the core of the now bouldery type surfaces have not been exposed to water and hydrolysis, the process of adding the H2O to the matrix of the mineral matter to create a new mineral. And finally, chemical weathering, also referred to in this case, the third type, carbonation. So our third type of chemical weathering, carbonation. So this does not involve so much oxygen or water, but carbon dioxide. So in this case, we have rocks that have carbon in them. They have carbon dioxide in them, or carbonate rocks of various types, interacting with water. So the water can basically dissolve some of these rocks and create these underground caverns as the water flows through and takes the mineral matter away. But also we get slow drips of water that have come through the in this case limestone rocks, which have calcium carbonate within them, and extract the carbonate and deposit them within the caverns below. And that would form these slow drips that evaporate the water away, leaving the carbonate materials behind. It would leave us with stalactites, stalagmites, and columns. You're probably familiar with those. Here's a nice picture of stalagmites growing from the ground up, stalactites coming down from the ceiling, and all kinds of features that we see within these limestone caverns. If you haven't had a chance to go visit any limestone caverns in your lifetime, please go do it. It's absolutely phenomenal landscape, or I say subterranean scape, that is definitely worth exploring. There are many all over the world, in the United States, in the uh, the border of the Czech Republic and the Slovak Republic. Some beautiful, beautiful caves there. So go see the world, go see these caves. Our last form of weathering is referred to as biological weathering. And this is where we have biological activity of plants and animals that help to physically break down rock material. In this case here, we see the roots of trees have grown through what would have been smaller cracks, and as a tree has grown, as the roots grow, it can crack those rocks open, lift them up, etc. We see that in two separate pictures here. And that is something you have to be careful at home too, because if you put a tree very close to your house foundation, it can actually lift the foundation up. You've probably seen sidewalks or even driveways lifted up by the roots of trees as they've grown from smaller 6 foot or 8 foot high trees to these 40 or 50 foot high trees with huge roots. And of course, as a tree grows, the roots grow, and that could undermine your house foundation and be a big problem for you. So you need to be careful there. The other portion of biological weathering involves a process of bioturbation. And basically, in this diagram, we're seeing the leaves on the upper portion of a soil here, the humus layer, and a couple of horizons. And we see basically that worms are digging holes through these soil layers. And those worms, in this case, not only are making the holes, but those holes then become a conduit for air, oxygen, water, etc., to interact with the soil particles and the rock material to more quickly turn rock into soil, or to help weather that rock material from larger pieces into smaller pieces. So biological activity is an important component of our weathering trio: the chemical, physical, and biological. Something to keep in mind in weathering is that not all places experience the same amount of weathering. In, typically, we can say that places that are warm, because chemical reactions occur faster when it's warmer, and when it's moist, chemical reactions also occur, as do biological actions, occur more so or more quickly in the presence of water. So we can see that places that are both warm and moist are going to see weathering occur on a much faster scale than places that are, let's say, the opposite, dry and cold. So dry, cold places are not going to see weathering occur as quickly as warm, moist places. And we can sort of get a proxy of this weathering capacity in terms of this diagram showing climate type running from tundra, so we're going from sort of cold, dry places all the way off towards the right side of the diagram to the tropical rainforest, or the tropical wet climate type. In this case, what we see is we have a very deep depth of weathering in a tropical wet environment, so a place that is very moist and very warm. We get relatively shallow depths of weathering in places that are, in this case, the deserts, hot and dry, so we don't have enough moisture there. We increase the depth of weathering into the mid latitudes where we get somewhat mild temperatures and abundant enough moisture, but then also the depth of weathering also decreases as you go towards the tundra and beyond, where we have very cold and quite dry environments. Now, if we went further into the polar environments, of course, we're now dealing with glacial weathering, and it depends a lot on not just the environment, but whether the moisture content, the temperatures are allowing for glaciers to move or not. So mass wasting, another portion that we need to talk about. So weathering is breaking down of rock in the three ways that we talked about, either physically, chemically, biologically. Mass wasting refers to the movement of rock material from high places to low places, mainly by the actions of gravity. So we're talking about things like landslides and debris flows and slumps. And what we can see in this initial diagram or introduction here is this diagram is showing different types of mass wasting events from the very slow to the very fast in terms of how quickly these occur. In the slow side, we have solifluction and creep. So soil creep is something that we get even in the LA area. Solifluction more so in very cold environments like permafrost areas. Slumps, also called rotational slides. We get those in the LA area too. Lahars and mud flows. Well, a mud is basically silt and clay that are entrained in water. So it's a mix of water, silt, and clay. Well, if the silt and clay materials originated from a volcano or from volcanic materials, we would call that a lahar if it starts to flow. Debris flows, those we'll see in a second, are basically channelized flows of silt and clay and sand and gravel and boulders and whatever the heck is caught up in this very viscous or very gooey flow of water and anything else caught in the water, typically after a big downpour from a thunderstorm or a heavy winter storm. And the fastest of all, we would see rock falls and landslides. So we're going to talk about these in this order, from the slowest to the fastest. And a few things to keep in mind as we're having this conversation is that the mass wasting is, or the type of mass wasting is heavily dependent on a few factors. One of those being the earth materials. We can see that crystalline rocks, like metamorphic rocks, igneous rocks, can form some very, very high cliffs because the grains have been formed or forced together so tightly that they are very hard to break apart. And they can stand up to very, very high cliffs. If you think of the cliffs of Yosemite Valley, those are granitic cliffs made out of granite, and those are very, very steep for thousands of feet. On the other hand, if we had sediment or rock fragments, they are not bonded together sometimes at all. So in that case, they are dependent upon the angular nature of the grains themselves, which in part is related to the size of the grains. We can see that we can build a big, tall mound out of, or taller, steeper mound out of boulders that we could out of sand or out of silt. But it's even more complex than that, because if the sand is wet, we can get one angle. In fact, this diagram is showing that over here, that sand that is, let's say, fine sand that is dry versus wet. Wet sand is always going to be able to have or build up a higher angle than if we had dry sand. And you think about that if you were building a sand castle. If you had very dry sand, you can't make a vertical face out of that sand. But if you had wet sand, so the water is helping that sand to bind a little bit, either through cohesion of some of the finer grains in there, or just the nature of the grains themselves and their ability to stick together by just friction. We can see that moisture therefore plays a role. The type of material, be it boulders or fine sand, plays a role. And also, are you in a geologic setting where we get frequent earthquakes? Because earthquakes can also trigger mass wasting events. So we have to keep that in mind when talking about mass wasting, that not every environment is created the same. Another key factor is water content. And water, the presence of water, will allow the water and the silt and the clay to flow if given the chance. Water is a fluid, and anything trapped in it can actually um, move in a fluid way if there's enough water. I'm talking about a lot of water, like we're talking a, a flash flood event. Water, by the way, also has weight. Every cubic foot of water weighs somewhere in the order of 60 or more pounds. And if we add that weight to a slope, especially the upper reaches of a slope, that weight is going to exert a force downwards and help landslide movement. So the weight will allow slumps and slides to occur more easily. We can also see that water, in the presence of fine grained materials like silt, especially clay, or rock materials that were mainly clay materials, so shale, etc., water will allow the surface of those earth materials to become more slippery. And think about that. If you walk on clay that's dry, you usually don't slip. But if you walked on wet clay, you have a really good chance of slipping. So you want to avoid areas of wet clay if you're walking anywhere after storms, etc. Now, that water can make a slide plane. In this example here, I see there's a slide plane where water has made this area very wet, and that's going to make it more slippery, more slick, and therefore a landslide or a slump could occur more easily. And we see that because of this, landslides and other mass wasting events are more common in the wet season or immediately after a wet season when infiltration is still occurring. So water is a very important component. We have to keep that in mind all the time when discussing these mass wasting events. So again, we're going to run from the slow to the fast. We're going to talk about soil creep, slumps, mud flows and lahars, debris flows, and finally rock falls and landslides. So soil creep. Remember, we're going from slow to fast now. So these are slow movements of weathered rock material down a hill, usually only in the upper few feet of weathered material. Um, I'm told typically we're looking at maybe up to 4 feet or so would be a typical depth for this movement. And slowly what's happening is gravity plus moisture is allowing the upper layers of this weather material to slowly, I'm talking years and years, to move downhill. And some of the giveaways to this occurring would be telephone poles that have tilted. We can get walls that have been displaced. We have fences that are tilting. So these are some of the key giveaways. And if you ever drive north of Santa Barbara along the coast, you can see the rail line running along there near Gaviota. And also you can see lots of areas where the phone lines or the telephone lines close to the rail lines have all tilted. Fences have been tilted. So keep an eye out next time you do that drive north of Santa Barbara. Rotational slides occur a little bit deeper. Now what's key here, a rotational slide or slump, we have a kind of a concave failure plane here. So the rupture occurs on a concave pattern. So typically we'll get this. This is a bit faster than soil creep, but this could take years for a slump to move slowly. And of course, you don't want it to be building down below or up above it or anywhere near these. So basically, the weight of the water, the slickened surface, allows this rotational movement down slope. We can often see a scarp towards the top, the head of the slide, and the toe or bottom of the slide here as accumulation of this material that has moved down slope. So in reality, we'll see slumps or rotational slides look like this photograph up here in the upper right. Mud flows, now we're getting a little bit faster. These are entrained in water. So we have typically fine-grained materials flowing downhill during a storm, right after a storm, when we've got a heavy downpour where the rate of infiltration is exceeded by the rate of precipitation. Now, these will flow down and these can do tremendous amount of damage. They can wipe out villages because they're taking material from, especially if there's steeper slopes, and moving that material down slope, but typically finer grained material. And if that material emanated from a volcanic source, so it could be the ash that was laid down by a volcano, hundreds of years ago. If that gets entrained, it gets picked up, it gets removed or eroded by flowing water and moved down slope, we would still call that a lahar. Otherwise, if it's not volcanic in nature, that fine-grained material or the actual mass wasting event would be called a mud flow. Now, typically mud flows can pick up coarser material, but if we get enough coarse material entrained in the mud, then we would change its name to a debris flow. Speaking of debris flows, now we're talking mud. So again, the silt and the clay entrained in the water. But this time it's moving fast enough to carry boulders, gravel, trees, parts of buildings. And we see a lot of that mixed debris dumped at the bottom of a debris flow. So oftentimes the boulders will be exposed quite a bit. And so we can tell that was debris flow that came through and not a mud flow. So that's the term debris. It's kind of a mix of everything, and these move quite fast. You've got to be very careful with these, and because of the boulders and that slurry of water and sand and gravel all together, it's very, very dense. If you try to walk across even a very, very shallow debris flow, you'd be in big trouble because the density of that material moving at the speeds it does, maybe could be 30 miles an hour. In this case, you would be in big, big trouble. So just don't do that. Some people have tried to cross these in cars, and the cars end up miles downstream. Not a good idea. We have landslides getting towards the end here. Now we're really picking up on speed because landslides can happen very, very quickly in a matter of seconds or minutes. So something would trigger the landslide. Sometimes that's, by the way, a seismic event, but more often than not, it's an event following a particularly wet winter and slicking of a slide plane, the weight of the water, all of a sudden we would see the slide move downslope very quickly, like the one in La Conchita, California. Actually, it's happened multiple times where the slide has occurred and basically the hillside has moved in less than a minute from the upper reaches down towards the coast in this case, or the valley floor. So always looking for these planes of weakness, especially if bedding planes are tilted downhill. So we have a slope dipping down towards an open area. So easy for the wet or slickened beds to slide down or downhill. Now, unlike a slump, this is not rotational. There's no convex shape to the slide plane. This is on a flat slide plane. That's the difference between a slump or the main difference between a slump and a landslide. And in this case here, we're looking at a linear failure plane. And then rock falls. Well, that's exactly what is occurring here. The rock is falling. So if rock becomes displaced from its bedrock source, we can see in a very very fast, few seconds to minutes, rocks from the upper face falling down to wherever it's flat enough for them to rest. This could be miles, or it could be a few hundred feet. Whenever you've got steep terrain, this is something you have to be careful about. So anytime that you're traversing a mountain road in a car, you've got to watch out for rocks, especially during the winter season, but this could be any time of year. And again, this could be triggered by an excessively wet winter, an excessively cold morning that starts to warm up. So freeze thaw is in action, and as things thaw out, maybe the rocks are going to spall off or fall off from the cliff face. Or it could be from a seismic event. Maybe there's a little bit of a tremor and it's going to loosen some of the rocks or displace the rocks that are already somewhat loosened by the other processes. Now, at the base of cliffs, we will often get the fallen material accumulating. And it is a word I'd like for you to know, that talus or talus. In this case here, this is just an accumulation of rock material that we find at the base of an area of rock fall. In this case of this picture of Mount Rushmore, of course, this was accentuated by the sculpting of our presidential faces there. But even in a natural environment, we would have a scar from rockfall and talus or talus always accumulating at the base of that. So big chunks of rock at the base of the scar, evidence of rockfall, would be called talus or talus. So these are the most common forms of mass wasting that we've discussed, from creep to slump or rotational slide, lahars and mud flows, debris flows, and rockfalls and landslides. So slow to fast. In all these cases, aided by the presence of water, but gravity doing most of the work. Okay, so we've talked about weathering, we've talked about mass wasting. Next up will be erosion, the removal of loose material, typically from uphill to downhill places by water, ice, and or wind. And we're going to break those down into the different components. So as we move forward, always keep in mind where you are in the chapter and how it fits into the general scope of the course. Take care and be well. Hope you enjoyed this. Bye-bye.